Where are you going? Huh? No, I'm going to give the lecture. Yeah, but you should stay. I mean, I can't force you, but whatever. Hello. Hey, one viewer. Huh? Well, I'm going to change it to the presentation a little bit, but hey, we're up to 6 people. So hi, welcome to campus, people who are actually here.
You could record the lecture.
I think it is recording. It will post happily on my YouTube account after this, whether I like it or not. Tied to my Google Plus account and cross-posted on. I don't think it'll cross-post on Twitter because. Anyway. Can somebody online type in the chat and say whether or not you can hear me? There's 10 of you now. Somebody should type in the chat. No one? Are any of you in the? Need to get my point across, so I used a lot of punctuation. Can no one else see the chat? That's the problem. Oh, that would explain part of it. Somebody commented on the Google Plus Hangout, I can hear you. That's good enough for me. And you can hear me, so. Well, this may not be the most interactive lecture I give. Hey, look, it's my lecture. Okay. We'll just give this a go. Hi, everybody.
Hey, guys.
So I'm glad that some people actually showed up to the room, even though I am also slightly disappointed because I was planning, if nobody showed up, because nobody was here when I got here, I was just going to sit the entire lecture. But now I have to stay. Anyway, so I can ask the 7 of you how project 1.1 went. No complaints as of yet. I'll assume everybody online just loved it and wanted more of it. They're not here to object. All right, so we're going to be talking about various additional ways we can interpret sensor data. So one term I didn't introduce you guys to before is dead reckoning. And so actually has nothing to do with zombies, but I felt like putting a zombie on the slide. So dead reckoning is when you are essentially doing open loop estimation of where you are. So if you assume you know your speed at one particular position, or sorry, you assume that you know your particular position at some point in time, and then you just integrate, you know what your speed is, you know what your time is, and then you estimate what your new position is based on that time and speed. And so this is a common technique. It's the first part of part 1.2 project. But the real problem is that the errors accumulate over time. The more you do this, the further that you get from your original home position, and the more and more the small errors are going to accumulate. You're going to make more assumptions, and eventually your estimate's not going to be very useful at all. So, but what this means for the actual project, just to go into it in a little bit more depth, is that for the polygon, the first approach, the open loop approach, is you drive m meters and then you turn x degrees or radians or whatever you have. So you would start out down here, drive forward, turn, drive forward, turn, drive forward, and turn. I mean, that's what you should be doing in either case, but in the dead reckoning sense, what you're going to do is just set your speed for a set period of time and have the robot drive at that speed until the time is up. And so the way that you get the robot to drive is that you publish twist commands. And so twist is the general name for applying velocity to an object. You can, in the general case, you can apply it in 3 linear directions and 3 angular directions. But really, for the turtle bot, the only thing you're going to apply is X linear direction, which means go forward, and Z angular direction, which means turn around some. And so driving the actual robot, what you're going to do is you set some rate for how often you want to send the messages, and then you grab some initial starting time point, which we're saving as t, and then we're comparing the current time, which we get with ROS-Pi time now, subtracting the old time will get us how much time has elapsed since we started this, and we compare that to some set number of seconds. And so if we do this loop, this loop will run for however many seconds number of seconds is. And then you just constantly publish your twist message, and that will make the robot drive that far at a certain speed for a certain amount of time. And then you sleep so that you're not constantly sending these messages. That would overwhelm the communication system, if you were sending them 1,000 times a second. So really you just set a rate, and here we have it at 10 times a second. Now the other approach is to integrate some of the sensor data. And so dead reckoning just assumes that your commands worked. And what you really want to, and if those errors accumulate, the square that you drive over time, it's not going to continue to be the same square, but shifted slightly, and you get some sort of spirography pattern where the square just doesn't line up time over time. Is spirograph a totally dated reference, people in the room? Do you know what spirograph is? Yeah, show of hands, yes. And no. That's the rest of you. Yeah. Oh, yeah, I mean, it's a toy that I had when I was younger. Anyway, we'll just, that reference isn't important for understanding of the lecture. Errors accumulate over time. So instead, what you should do is use the odometry. And so the odometry is a message that the base robot driver, regardless of platform, is going to publish. It's going to tell you information about what the robot thinks it's doing based on its sensors, primarily just the shaft encoders that are checking on, how far the wheels have turned. So this isn't a absolute estimation of where you are, but it does have some useful information. So you can see, like all messages, it has a header, and then the additional information that it has is a pose with covariance and a twist with covariance. And so that's going to tell you what the robot's estimated position is relative to some point. That some point is a reference frame in itself, usually called odom. So there's going to be some position relative to basically where you started the robot, where you turned it on. That's going to be its odom frame of reference. And so all the other positions are going to be relative to that initial position. And then it also gives you an estimation of its current velocity, and you can use that as well. And so what you should do for the second part of this assignment, when you're actually trying to drive the robot, is to do a closed loop, including the information from the odometry message. So the essential structure of the algorithm remains essentially the same. While true, drive to the next point, and then turn so you're facing the next point, drive there, turn, drive there, turn. But more specifically, when you drive to the next point, this is where you're going to implement your basic proportional control. So what you're going to do is until you reach the end point, you're going to calculate your difference between where you currently think you are and where you want to drive to, one of the points on the polygon. And then if the difference between them is small, you move on to the next step. So if we're already at that point, or at that point with some small margin of error, then we're going to then turn and then move and so on and so forth. Otherwise, you set the velocity command proportional to the difference. So if you are, a full meter away from the point that you're trying to get to, full speed ahead. If you're only a couple inches away, but you're still not close enough for your or whatever margin you consider reasonable, then you don't want to set full speed ahead. You're going to set some proportionally smaller velocity. And then you do the same thing when you're turning, but turn instead of drive forward. 7 people, does that make sense?
Would you want a proportional gain on your turning velocity so that when you're getting closer
Mhm.
to that you turn?
Yeah, so you do a proportional on both sides, but it's the same process, so I didn't write it out twice. And that's all you have to. That's all you have to implement from X. It's as simple as that. All right. So then can we do better than this? Is there a way to estimate what our current position is using more than just odometry? Because as we know, there could be additional factors of slippage between the wheels and the ground, or somebody kicks the robot, all sorts of factors that could move the robot farther away from where it thinks it is just based on the odometry alone. And for that, you can use some of your other sensors, the range finders and things like that nature, to help estimate the position. So one easy thing to do is if you think that you are currently a meter away from a wall, or you think you're in one spot and at that time it looks like you're a meter away from the wall, you think you move half a meter forward, but then it tells you that that wall is now a quarter of a meter away. You know that your odometry isn't quite accurate. And so then you can adjust based on what your sensors actually say. And we're going to talk about how to do that more accurately in coming weeks. There's a lot of probabilistic ways to estimate what your position is over time, things that people who have taken AI-specific courses will know as doing Monte Carlo localization, where we basically just guess a whole bunch of possible places and figure out which ones of those are the most probable given our sensor data, and then we refine our estimate over time. But we'll talk more about that in coming weeks. So that's the quick rundown of what the latter part of assignment 1 is for this week. And now what I want to talk about is just different ways to interpret sensor data and how to store sensor data. So there's a big trade-off in how you store sensor data between the space that you use for the data and how easy it is to use. So there are ways to store the data that is efficient. It doesn't use much space, but makes it a lot harder to use. And so we're going to sort of see the different ways we can publish the data from our sensors and how useful that data is. And oftentimes the trade-off here, the ways to use or less space, is to use some bit of the data structure to actually imply more information about the data. And you'll see what I mean by that in a second. So let's start with the laser scan. So the laser scan message here, we saw this before. It has a header. Then it has a bunch of sort of meta information about the sensor itself. So it has an angle minimum, maximum, information about the increment between these angles, and so on and so forth. And then the actual information is stored down here in a set of 32-bit floats that represent the ranges. And so we can say where each of these lasers hit just using this structure. And we can figure out what those points are with a simple sort of loop like this. So for each of those ranges, we can index into that array. We can say that the angle to that ray is the minimum angle plus the angle increment times I. So this is what I mean when I talk about using the structure of the data. Since the laser readings are ordered in this sense, in that we know that the first one is the angle minimum and then the next one is right next to it and so on, we can use that to efficiently store the data. And then when we want to translate it into XY space, it's just simple trigonometry. Say that the X position is the cosine of the angle times the range, and the Y position is the sine of the angle times the range, where range really is range bracket I. Okay, so here we have two different ways of storing the data. With the laser scan, we store this information as essentially n different floating point numbers, where n is the number of ranges we have. If we were to keep track of this as a set of points, each of them is going to have an x coordinate and a y coordinate, at least. And so then that's going to keep twice as much data. And so usually you see the laser scans published in this laser scan form that you see here, just because it takes up less space and uses that structure of the fact that they're in an order to make the amount of data you store smaller. But the advantage of that, or disadvantage, is that, you know, if you want to figure out is your robot about to collide with something, you have to translate it from essentially its polar coordinate to its XY coordinates, which is not as convenient. The other thing is you kind of have to keep those points in that order. If you wanted just a subset of those points, say the set of points that represented a particular obstacle, you couldn't really keep them in the laser scan setting. You would have to get a subset of them, and that's where the set of points is actually a more efficient way to represent things. Okay. Now, for laser scans, there's not that much data overall. I mean, you do get a lot of laser readings from typical laser scanners, but the actual magnitude of that data is not that great. Where it gets trickier is with images, and specifically images that you get from the Kinect. So here's the message definition for how we store images. So we have some integers that represent the height and the width of this image in number of pixels. And then we have some encoding, information about whether each of these bytes is big endian, depending on the encoding. And then the actual data is stored down here in an array of unsigned 8-bit integers. And so the way this might actually be used is, this is an image that I took off of my laptop webcam today. So you can see here's the timestamp. If you translate that, it translates to sometime earlier today. It gives you a frame of reference. And this is a 640 by 480 picture encoded in RGB8. And we'll talk more about what that means. And then the data is just this sequence of numbers. And ultimately, you end up with 900,000 different numbers in that array. And the way to interpret that is that, so 640 by 480, that means that we have a total of 300,000 pixels. And RGB8 means that each of the numbers that we're storing in the 8-bit, each 8-bit thing is going to be a different color value. And so we end up with having 24 bits per pixel. And so the 640 by 480 times 3 color values for each pixel gives us the overall 900,000 int 8s that we need to represent this image. And so if you look at the bottom here, what these numbers represent is the first pixel is 45 out of 255 red value, 32 out of 255 green value, and 28 out of 255 blue value. Combine those, you get a color. That's the color of the first pixel. Clear? And so then there's other ways that you can use the image type to represent different sensor readings. So the Kinect that each of the TurtleBots has also represents the depth data as an image. So again, this is a 640 by 480 image, but each pixel is going to represent a depth, happen to be measured in millimeters. And it's stored as an unsigned integer with 16 bits. And then, so the actual data down here is going to be, you combine the first two numbers into a 16-bit integer, and with that, you can represent the actual depth. Does that make sense? So instead of color values, the image is storing at each pixel a different depth. Now the tricky part here is that, well, one of the nice things about the image encoding is that it's storing all of this information, again, in an ordered way. Just like the laser scan was saying, okay, each successive number is a different laser scan, but they're in an order. Here, all the pixels are listed in order in the data, so we know, okay, the first one's the first pixel, the second one's the second pixel, and so on. And then we can combine that information to figure out where things actually are. So just look at all the data that the full connect will spit out. Each pixel has 3 color values associated with it, and then each of which is 8 bits. And then each pixel also has a depth value of 16 bits. And so sum total, each pixel has 40 bits. Then you have to think about that for the thousands of pixels that we have in the full image. And it ends up being, give or take, 1.5 megabytes of image for each image that the Connect spits out, both color and depth. Okay, but then keep in mind that the Connect is constantly running, and you can run it at 30 hertz, and then you get 46 megabytes per second. And so that's a lot of data. But it's not quite as much as it would be in other representations. So to actually figure out where these images correspond to, if you say want to get the pixel, the color of pixels in space, you could combine the pixel location, so it has some row and column, which we'll call I and J, combine that with the pixel depth that we got from the depth part of the image, and then use the camera's calibration info to figure out where that point would be in real space, and then you can get the X, Y, Z, and then you can associate the color with that. That transformation sound good? So then, let's look at the other ways we can represent this data. So the image format itself is ordered, and it's not as easy to use in lots of cases as something like a point cloud. So a point cloud is like the list of points we had before, has a header, and then just keeps a list of points, and associated with each point is an XYZ coordinate. So this is the standard way to keep track of a set of 3D points. And then there's this additional information, the channel float channels, and that's going to be where any additional information beyond position would be stored. So you might have one additional channel that keeps the RGB information, and then you can pack the 3 RGB values into a 32-bit float somehow. And then, so you can match up the points with all the values in the values array in the channels to figure out the XYZ and RGB of each of the points. So this is a less efficient data format in that this is a bit more verbose about where all the information is. So you need to specify by specifying the exact XYZ positions and also the additional color information. And so transmitting point clouds is going to take more space than just transmitting the two camera images that we saw before that the camera transmits. But this is easier to use, more flexible, and has all of this information in one space, whereas in the other ones you have to combine it with the camera information and all that. This is not the most efficient. So because of the inefficiencies of this way, the people who made raw, so this has 128 bits per pixel. Compare that with our 40 bits per pixel of the last one. Since we're explicitly saying what the XYZ is, that takes up a lot more space. All right. So the people who made ROS realized that that wasn't the most efficient way to pack the data into a set of bits. They went out and tried to find more efficient ways to represent this data, and the point cloud 2 is what they came up with. So again, this has a header, and then what it, I'm not going to go through bit by bit what actually is packed in here, but basically it specifies its own bit coding to say, okay, this array of unsigned integers, 8-bit integers data at the bottom here, that's going to contain all the information with a structure we specify with this above information. And so it will, pack in one channel for X, one channel for Y, one channel for Z, and then you can pack in arbitrary additional channels for color and things like the normal vector or weight or whatever it happens to be that you think is more efficient to store in this structure. So as you use the different data structures that are provided by the Turtlebot, just keep in mind which ones are going to be easier to transmit over the wireless. So that's the real reason why I want to talk about all this, is because transmitting the images alone is very simple. It has, whatever I said, 1.5 megabytes per second, but overall, that's a lot less than transmitting all the XYZ positions over time. And I've actually verified if you go to lab and try to view the camera images, you can. It's a little bit laggy, but not horrible. Whereas if you try to view the point cloud, which is the much nicer data structure, it essentially chokes the network structure. We don't have that much bandwidth in that room, and as a result, can't really visualize it as easily, especially not at something like 30 hertz a second. Sorry, 30 frames a second. Okay? So from the sensor, you're going to get your streams of data, whether they be in laser scan form, point cloud form, or something else. Then comes the question of what are you actually going to do with it? And so, if you resolve your image into a bunch of pixels or a bunch of XY points, there's two common operations that you have to go with from there. The first one is segmentation, which is basically classifying each of the data points as in one category or another. So here you see an example of image segmentation where we have a lovely picture of an Asian landscape of some sort. I should have actually figured out what this was. And then using different texture filters and color filters, we can segment it into a bunch of different segments, saying, okay, these are trees, these are the dark trees, this is the building, this is the sky. So we've classified each of those pixels into some category. And then, from there, we can start to make more assumptions about what we would do about this picture. And so segmentation is the first step. And then the second one is doing feature extraction, figuring out, okay, I have these points. What do they actually represent? What feature can we extract out of this set of raw data points? And so segmentation, there's a couple different ways you can do it. One of them is by subtraction. So you know what the base image is, and then you have some different image. You want to segment out some set of that image, and you can just do it by taking a difference between the two images. So you see image figure A here and figure B are essentially the same, except for we have the guy standing there, and we can segment out the pixels that correspond with the guy by basically taking the difference, and the result is figure D, which is not a perfect representation because he is wearing a blue shirt in front of a blue pillar. And so we don't get a perfect idea of exactly which pixels represent him, but it's one place to start. So the requirements for this is you need 2 pictures or 2 pieces of data. You can do this with laser scans or point clouds or whatever. And one of them has the feature that you want and the other one doesn't. That's how you do subtraction. You can do this with only 1 picture if you know what the background is going to look like. The most common example would be blue screening. You can pick out the foreground actors by just saying, okay, I know the background's blue. We're just going to subtract that. So that's one way to do segmentation. And there are other ways, but we'll talk about them in time. Then you have to do feature extraction. So one thing you might want to say is, okay, I know that keeping track of all of these individual points is going to take a lot of space. So let me just abstract them into a line. And so there are different ways that you can do this. So say you have an exact set of points, you can fit a line to it just by by fitting a line to it that minimizes the sum of squared errors. But there's additional operations on top of this beyond just fitting a line to it that we might want to consider depending on the amount of noise that we have in our data. So there, I fit a line to it. One might be, so we have a bunch of data that might not necessarily all be fitting into a line. And so there's this one algorithm called split and merge, where we will segment a bunch of bunch of points into a number of different line segments. So I'm just going to talk through it first, and then I'll show you an example. So we start off with our set of points, and then we obtain a line by passing that passes through the 2 extreme points. So 2 points that are the furthest from each other. Then we have a line between those 2 points, and then we find the point that is most distant to that line. And if it's sufficiently far away, we split. So let me skip ahead and show you what that looks like. So here's our data points. This might be like the corner of a room or something like that. And each of these represents, let's say, a laser read. Looking down from above, we'll say. So we find the 2 most extreme points and join them by a line. Then we find what might be the most distant point from that line and measure that space. It should be perpendicular, but I was limited in my PowerPoint drawing skills. All right, so we pick that point, and since it is sufficiently far away, we're going to split based on that point. And now we have 2 new line segments that split on that point. And from there, we have 2 lines that better fit this data. With me so far? And then we can go ahead and do it again if we'd like. So for each of these lines, we pick the most distant part, and then we can split those lines into new lines. And then we get 4 lines that represent this set of points. Now, my 7 people. Wow, those points are really thick. Anyway, sorry. 4 people, or 7 people. What could be made better about this set of lines representing this set of points? So we could also make a representation that had tons of line segments and went point to point to point to point, or something like that. We could reduce the error of the set of line segments by increasing the number of points, but that doesn't really get us a more efficient representation. Still a good point. We could possibly come up with lines that better approximate this set of points. Any other ideas what we could do?
Whether there's
Yeah, merge the two middle lines. Those two middle lines are almost a straight line with each other. And so flipping back to the algorithm for a second, this algorithm does happen to be called split and merge. And so we merge. So if two consecutive line segments are close to each other or collinear, meaning roughly point in the same direction, then we can obtain a common line, find the most distant point to that common line, and if the distance is smaller than some threshold, we go ahead and merge. So just an example of that. See here, we have those two lines that are pretty much in common. So we draw a new line that goes through the 2 points, and then the distance to the farthest point is quite small, and as a result, we merge into those 2 lines into one. I didn't mean for the other lines to disappear, but so then you would have just 3 lines that represent all 3 or all of these points. And then from there, you could start to estimate something about the geometry of this room. Say if you estimate where all 4 walls are, then you can say, okay, this is a room of size whatever, and start to do higher level reasoning on it. But in order to do that, you need some way to start representing the points as higher level structures. Okay. There's other ways to represent lines, or to find lines in a set of points. And I'm not going to go through all of them. One of them is ransack, unrelated to the verb ransacked, i.e. go hurriedly through a place, stealing things and causing damage and mayhem. But ransack is a way to find a line or a model that best fits your data while ignoring all other points. So let's say we know there's a line somewhere in here, but we have a bunch of spurious readings. Ransack is a method that is both iterative and non-deterministic that will basically try a bunch of random different lines and find a model that finds the most points that fit on that line. So it basically tries random things, see how many points fit that model, and then tries again, keeping either rejecting the new model or making a better one. And if you run this enough, you'll get a model like this, which is they will claim is the best fit. Okay. Other ways to find lines is the Huck transform. And so I think, or on the next project, this is what you'll be doing a little bit of, trying to find lines in sensor data that you get. So this was originally used in bubble chamber image analysis, so basically watching floating bubbles, trying to find patterns. Originally, it was used just for lines, trying to find lines in images by Duda and Hart in 1972, and then it was generalized to be able to find arbitrary shapes in images by a guy named Dana Ballard in 1981. Reason I mentioned Dana Ballard is because A, we'll be talking about his method as well, but also he was one of my professors at University of Rochester. So he's now in Texas, but he's a cool guy, so I mentioned him here. Anyway, so we can represent straight lines with the equation kx plus m. And we could search through all possible lines that go through all the points that we have in xy space, but the approach we're actually going to use is to search in km space. So basically looking at all possible lines in all possible intercepts and all possible slopes. So for example, let's say we have these 4 points and we want to find a line that goes through most of them. All right, so what line would you pick? My 7 people. Just one that basically cuts down the diagonal. This one, which has the equation negative x plus 4. So we could, so this is where we're going, is that the answer is negative x plus 4. That's the line we want to find because it goes through 3 of our 4 points. But what we're going to do is we're going to take each of these points and come up with an equation that represents what lines go through them. So the general form is y equals kx plus m. And then we can just use our standard algebraic manipulation once we plug in one of these points, in this case 4, 3, to say, okay, that's equal to 3 equals k times 4 plus m. And then we can come up with plausible lines that go through that point using the equation m equals 4k minus 3. So if we picked an intercept, let's say 3, we could plug that in and figure out a line that went through that point. So then we can map that into a line in MK space. So just as we use two variables, x and y, with set values for n and k to graph a line in xy space, here what we're going to do is take the equation m equals 4k minus 3, apply and use those two variables that are set and come up with a line that goes through MK space. And so the line in MK space for the point 4, 3 looks like that. The line for the other points we can add in looks like that for the 3 points that the line goes through. And note that they all intersect at that one point. The line for the point that isn't going to be on our final line ends up looking like that. So we can come up with a hypothesis line that we want to use by noting that all three of these lines intersect at the point m equals 4 and k equals -1. Plugging that back into our original formula, y equals -x plus 4, that's the line that we were looking for. So we translate into this other kind of space, and then we look for the point of greatest intersection, and that's the line that is going to best fit our data. Make sense? 7 people? Okay. Any guesses why this is not the actual approach that Duda and Hart used? So what can't you do with the form y equals mx plus b? Quadratics, like not straight lines?
Yes.
Okay. Excluding not straight lines.
3D. 3D.
3D. We could expand this to 3D. The problem is, what line can't you represent in that form? Yeah, straight up and down, x equals 2. So instead of representing lines in MK space, instead for 2 dimensions, the canonical way to represent lines in Hupf transforms is in sort of polar coordinates. So you specify an angle theta and a distance r. That defines a point, and then you have, or that defines a ray, really, and then the line is the point that is perpendicular to that ray, that goes through that endpoint. So think about it for a second. You can spin that around. For an angle of 90 degrees, you can get horizontal lines. Angle of 0 degrees, you can get vertical lines, and you can get anything in between. So now we still have each line represented by 2 parameters, but now the parameters are r and theta. So just a different space for representing lines. And you can go through and represent these lines in a different way, and then to figure out how they actually, what lines you actually want. It's equivalent to this equation for translating it into mx plus b form. But what you do is you basically parameterize your space. So looking on the right here, on one axis you have all the possible angles. On the other axis you have all possible distances from the center. You can tell I stole this slide from someplace British by the way that it's spelled center. And for each line that you would come up with through that space, you basically add points to a counter. So you can iterate over all the points on each line in the space, adding one to the counter, and then the places where there are the highest values are where the lines are going to be. So for example, this input image on the left here has lots of pixels and essentially comes down to 2 lines. And so lots of different lines are going to have some points on them. But you can see from the image on the right, there's clearly 2 points that have the highest values, and they represent the 2 lines that we see on the graph here. All right, so you'll play a little bit more with this next week. Actually doing the Huff transform for yourself to be able to figure out where lines are. All right, questions? So, lines are just the first step. Lines are just the beginning. And beyond that, we have additional shapes that we could use. So the overall algorithm for the Huff transform is for each pixel that we are starting. So each point in the original set, or if we're going from a color image, we can think about it for each pixel. We mark all the points in Huff space that correspond with possible lines r theta. And so we end up iterating through all possible values of r theta that go through that point. We can then generalize and think about it in terms of other shapes beyond lines. As long as we can enumerate all the different possibilities of things that would include that pixel, we can use the Huff transform. So instead of for each pixel marking all points in the Huff space that correspond with just those 2 dimensions, we could do it for circles. So all the possible things that match for a given x and y center and radius. And as a result of that, you get something that looks like this. So do a Huff transform on this image to try to find circles, and you can find all the circles in this image. So that means that instead of just having a 2-dimensional accumulator where you try to find the highest intersection of 2 values, you would instead do a 3-dimensional space that essentially figures out, okay, these are all the points that I have that correspond with a circle of this radius at this center. And that allows you to represent with some granularity all possible different circles. And that's the Huff transform. Questions? So that's what I got for today. Let me see if I can find if there's questions online. Did anybody find the chat? No. Hey, we're up to 16 viewers. All right. Let's see if anybody else contacted me via Google+. Just a bunch of notifications that people are, yes, going to my event. I don't even recognize these names. Okay. All right. Let's just call it there. Go enjoy this lovely cold weather. Oh, questions? Yes.
Do you know when the second half of the first project is?
Yeah, it's going to be Sunday.
Okay.
So you have 1 week to finish it up. And then we're going to get on to sensors. That is an unflattering image or angle.
Should have this screen.
When does this happen in the movie? Spaceballs, anyone?
Yeah.
Okay. All right, go home. Looking at now, sir. Everything that's happening now is happening now. If you have questions, you can post them on Piazza, people online. Or if you missed this lecture, I think you can actually watch it on YouTube. Okay, bye, people.